In the last session, we have seen there is a problem in this case. We should not write like T of 2. Actually, this is a T of 3 only. Okay. This is a T of 3. Because this is actually, we mentioned that. Okay. You can see instead of the Q3, Q2, Q1, Q0, we have taken the output as T3, T2, T1, T0. This is how we have taken. Okay, that's the reason why. So whatever the T3 output is there, the T3 output must go as S out. Okay, therefore S out will be taken by this particular T3 value. Okay, so that's what we have right here. If you write the instead of the TQ, if you write it, the Q SY is actually assigned with Q of 3. Okay, that's the one point. The second point here also, instead of writing this particular one, better we have to take 3. Okay, 3 down to 0. This is also 4-bit line actually. T0, T1, T2, T3. That means 4 flip-flops. T3 is the last flip-flop. Okay, so here we need to write. Here we have to write. Okay. T of 3 is assigned with T of 2, and S out is actually S0 is assigned with T of 3. Okay, that's how we need to. Okay, when you simulate this one, you will identify whether you are getting or not. Okay, fine. Now let us see some of the things here. Okay. Okay, we have written that concatenation operation that we have used. Okay. There is also another option. That option is actually shift left we have written and shift right I have written here. Okay. There is another option that is called using the shifting operator, shift operator. Okay. Here actually what we have used, here we used only concatenation operation. Okay. Simply whatever it is required that we have copied into this one. Okay. But shifting operator, shift operator is as shown here in this way. Okay, let me take this is the 9th one. Okay, let me copy this. Paste here. Okay, let me take this is the 9th one. I'm going to talk about universal shift resistors. Okay. So what the universal shift resistor has to do? What the universal shift resistor has to do? It has to perform all the operations, right? Okay. Actually, my intention is that I want to change this code actually. Okay, that's the reason I'm asking you to copy this one. Yeah, let me write here. For example, look at this one. 1, 2, 3. For example, this is the Q0, Q1, Q2, and Q3. Okay. If I want to shift from right to the left side, it is called shift left operation. That is Q0 has to come here, Q1 has to come here, and Q2 has to come here. And this is occupied with serial in data. Okay, so this is how we can also write. The Q is actually assigned with, okay, Q shifted by 1 bit position. Shifted by 1 bit position. This is called shifting operator. Okay, if you want to shift to 2 bits, for example, then just you have to write Q of 2 bits. Is this point is clear? Okay, this is another alternative. I'm saying that whatever we have seen in the concatenation operations, far better. It's not a problem. Okay. Otherwise, we have another option that we can use the shifting operator. Let us modify this code. Okay. What I can do, everything is the same, but better I can change with respect to, in terms of the QT only, I'll let me write. The T is actually the output of the flip-flop. Okay. So I'm going to change what? Only this portion I want to change, right? What I want to change? If reset is true, all must be 0. Else, what about Q? Q must be assigned by Q left shift by 1. Okay. At the same time, the LSP bit must be occupied with serial in data. LSB must be occupied with serial data. That is also we need to write. Therefore, here we can write the okay T in terms of T. I have written right. I'm so sorry. Please excuse me. T and T. Okay. T of 0 is occupied with what? Serials in data. First, it will shift, and then left shift. The vacant position is that the vacant position is filled with serial in data. Okay. Some unknown value will be there once it is shifted in that LSB bit. Now I have said that you have to fill with serial in data, that will be replaced. Unknown will be replaced with serial in data. If this point is clear? Okay, one important point is that whenever you use the two-step print, we have to use the begin and end. Okay, this is what we have to think about it. Okay, so let me change this one a little bit down. This also I want to write it here a little bit down. Here I have to start the begin. Okay, because two statements means we cannot write only one line, something like this. We have to write within the begin and end. So this option is also there. Semicolon is required, right? I've written semicolon. Every statement must be ended with semicolon, right? Okay. Next, what is the next one? For example, I want to shift the 2 bits, for example. Then what's your suggestion? I want to shift 2 bits. Okay. For example, these two cases, this is let me consider this is the first case. Okay, this is an option 1, and this is an option 2. Okay, this is an option 2. What is the first case option? What is the size of the 2 input data? That means 2 bits shifting means what? Okay, look at this one. For example, I want to shift to 2 bits, for example. Q of 1 will come here. Q of 0 will come here. This is the serial in data of the 1 bit and the serial in data of the 0 bit. 2 bit means that 2 positions are vacant, right? 2 positions vacant means we have to fill the serial in data of size what? 2 bits. Okay, point is clear. Okay, so therefore this is what is important for us. Now, how can we write this information by using a concatenation operation? Something like this we can write like this: concatenation of q 1 down to 0, we can write it there, and si. Okay, simply I can write si is actually a 2-bit data. I have to declare si as a 2-bit data. If you're not writing the 2-bit data, if you write like this, then it's a wrong. Please remember that, right? So similarly, what about the shifting operator? Q is assigned. This is what the Q. Now the Q is assigned with what? Shifted by 2. Sorry, it is a right shift operation, right? It is a left shift operation by 2. And what is SO? Is SO is a 2-bit or 1-bit? It should be 2-bit. As you wish, 1-bit you want to take it or 2-bit you want to take it, that's up to you. But symmetrical purpose, we are taking the two inputs as serial in and 2 outputs as serial out. Okay. Therefore, I'm going to consider this is actually 2-bit of what? So sorry. What is this one? Q of 3 down to another. So 3 2 will come out, and those values we are going to capture that. Okay. Please look at this particular. So now let us look at carefully about the 4-bit for the universal shift register. Okay, let me write here. So what it has to do, what universal shift register has to do. So that means it has to perform all the operations, right? What it has to do? First, parallel loading has to perform. Okay, parallel loading. PL stands for parallel loading. Okay, that means this particular shift register, has to perform parallel loading operation. Shift left operation has to perform. Shift right operation has to perform, and the data must be stored inside of it also. Okay, that means so holding also. Hold the data. Okay, if any register is performing these 4 operations, then it is called universal shift register. Okay, but you can remember that at a time only one operation has to perform, right? That means if you want to choose one operation at a time, what kind of signal we can use here? Selection line. Okay, that means this is an output and input is actually, okay, most important one is selection line. Okay, if the selection line is equal to 0 0, how many selection line variables I have, how many selection bits I have to consider? 2 bits, because 4 possibilities. 0 0 means this will be selected as an output. 0 1 stands for this one. 1 0 stands for this. 1 1 stands for this kind of operation, right? Okay, that means there is an information here that is called 4-bit data in signal. Data in signal. Then you will get 4-bit output. 4-bit output Q. So this is actually meant for what? This is actually meant for parallel loading of operation. So when it will be parallel loading, the moment if I write one selection line, right? One selection line. If the selection line is, so what is the size of the selection line? 2-bit. If it is 0, 0, parallel loading. If 0, 1, shift left operation. Shift left means serial in data is required, right? Okay, we need to have a serial in data. This serial in data is meant for shift left operation. Okay, assuming that. Okay, what it will produce only one output. That output is called serial out data for the shift left operation. Okay, single bit size. Similarly, we have serial in data is I'm using for the purpose of serial shift left shift right operation. I can use the same SI for the shifting shift right and shift left, but usually people will take the different inputs. Okay. Now, what you will get here now? Serial out data when we are performing the shift right operation. Okay. Please remember that all these things we are going to do under the clock signal is available, the reset signal is available. So the moment the reset signal is true, for example, then all the contents of the Q, SO, okay, SOs are all zeros. Okay. Most of the cases we keep the Q values equal to 0 when because the flip-flop contents we want to make it 0. Okay, I don't want to bother about the SO. Okay. Okay. So, and once the RST is not there, then depending upon the clock, okay, and depending upon the selection line, operation has to perform. So this is the top level module of universal shift register. Okay, let us write a block here. For example, look at this one. If the selection line is 0, 0, for example, this is the selection line. Okay, this is the output Q. One, two, three. Therefore, this is called Q of 0. Let me call Q of 1. This is called Q of 2. This is called Q of 3. Right? If you write what happened if selection line is equal to 0, 0, parallel loading. That means D of 0, let me consider D0, D1, D2, and D3. Okay, parallelly, the data will come and sit into this particular. Is this point is clear? Okay. What is the shift left operation? If you apply 0, 1, what is the shift left? That means towards the left side. Okay. What about this one? This position will be occupied with what? One, two, three. This is SIL. For example, SIL. SIL stands for this one. Okay. Unfortunately, I have taken a small thing. That's the reason why I'm writing this. Okay. Next, Q of 0, Q of 1, Q of 2. Am I right? Therefore, Q of 3 is actually having Q of 2. Q of 2 is actually Q of 1. Q of 1 is actually holding the Q of 0. Q of 0 is actually holding serial in Z. Okay. Next, if it is 1, 0, then one, two, three. This is a shift right operator. Q of 3, Q of 2, and Q of 1. Okay. So holding the data means what? 1, 1 if you apply holding the data. That means it remains unchanged, right? The content of this one is remains unchanged. That is Q of 3, Q of 2, Q of 1, and Q of 0. This point is clear, right? Okay. So let us do the internal structure of this one. Okay. How many flip-flops are required? 4 flip-flops. Okay. As you can see, this evident that the Q0 to Q3 means that 4 flip-flops are required. Let me take the 4 flip-flops. Okay. First one. Keep it here. Okay. So we start, this is the Q0, this is the flip-flop one. Okay. This is FF0, flip-flop 0. This is the flip-flop 1. This is the flip-flop 2. This is flip-flop. So which flip-flop is suitable here? D flip-flop is sufficient, right? Okay. So let me consider this is the D signal here, and this is the Q signal here. So D, Q, D, and Q. All are D flip-flops. All these flip-flops are actually active based on the enable and what is this one? Reset signal. Okay. All are reset signals. We have another input for the flip-flops. Okay. All these are all clock signals. Okay. Therefore, this is called reset. This is called clock. Okay. Now, the input to this particular flip-flops are different, right? Okay. This is the input. This is the input. And this is okay. What do you observe? So when the selection line is equal to 0, 0, all the D ins are connected to this particular D input of this one. Okay. Right. That means one input is required here, as you can understand. Okay, D of 0, let me consider. Okay, and for this one is also required D of 1. This one is also requires D of 2, and this also requires. Okay, this is for 0, 0 option. That means we need, what is the size of the multiplexer here in this case? 2 selection lines are required. 2 selection lines means that what is the size? 4x1 multiplexer, right? We have to use the 4x1 multiplexer. Okay, so therefore this is what the 4x1 multiplexer is required. We always look at this one. So what are the selection lines here? 2 selection lines. Yes, 2 and yes. So whenever 0, 0 is there, this is what the 0th input. This is the first input. This is the second input. This is the third input, right? Of course, 2 selection lines means the 4 inputs can allow. Something like this we have to consider. Copy. I want to take it 4 times. Okay, next one. Here also it is required. Here also it's required. So, okay, so this is actually connected here. This is connected at this point. Okay. Now, what is the second input? Can anyone? What is the second input? 0. 0, 1 is for the 0, 1. What is the inputs for the multiplexer? First input is serial in data. Okay. So for the simplicity, I'm going to write this one since I have written there. Okay, SIL, SIR. Okay. This also for the simplicity. I'm going to write this is L, this is R. Okay. This input should be SIL. What is this input? Q naught. Very good. Where this Q naught is coming from? Previous stage. Okay. It's from FF not నుంచి వస్తుంది. Next, what about this? Q of 1. This is Q of 2. What about 1 0 case? Second input has to consider. What is this one? What is this? Q of 1. Where this Q of in is coming from? Succeeding stage. This is called the succeeding stage. This is called preceding stage. Okay. Okay, that means higher order bit నుంచి వస్తుంది. Next, what about this? Q of 2. This is Q of 3. What about this one? Input SIR. Very good. What about the fourth one? Directly, just a kind of short circuit this one. The Q naught is directly Q naught. That means this output is only connected to this. Okay. Next to this one is Q of 1. This one is Q of 2. This one is. Okay. Now the output of this flip-flop mux is connected to whom? The output of this one is connected to this fellow. Now, is that output is connected to that one or not? No. Where we have to connect this input to the GPs. Very good. So this is the input to this particular one. Okay. Next, the output of this one is connected to the input of this. The output of this one is connected to this. The output is connected to. Okay. Now, what about the outputs? Outputs can be an individual outputs. This is called Q of 2. Sorry, Q of 3. This is the Q of 2. And this is Q1. This is Q1. Look at this one. What will happen if S is equal to 0, 0? Let us verify this functionality. 0, 0. All the D naught will be selected. And this is what will happen here? D naught, D1, D2, D3. The moment if you give the clock signal, all this D naught, D1 assigned to Qs, right? Okay. Now, if we apply 0, 1, what will happen? So this is actually serial in data will come here. Okay, serial in data will come here, and we'll get Q0 is actually serial in data. Next, what it will come here? Q1 will become here. Okay, and what is the output of this one? Q1. So Q0 will come. Okay, we are not going to write the short circuiting. All this is not required actually. Therefore, multiplexer will be taking care of that one. Will give you that. This point is clear. Like this, according to the selection line, it will select one input to all the flip-flops, and based on the clock signal, the data will be transferred into it. Either the shifted version అవ్వచ్చు, లేదంటే in its own output అవ్వచ్చు, or otherwise serial the data in if it can be a data in signal, right? Can you write the structural program for this one? Please take it as a homework, okay? And submit this as an assignment, okay? Lab assignment 1. Write the structural modeling for this universal shift register. And I'm going to write the behavioral model for this one. Okay. Let us look at how do we write the behavioral model for this. Okay. Let us consider this. So if you want to write this structural programming for the above, we know that we have already given the structure. Okay. So we need not worried about what is the inside of the structure. You know, how many components we have to use? Total, how many components? 8 components I have to use, right? Out of these 8 components, 4 are multiplexers. Another 4 are D flip-flops. Already D flip-flops we have done previously, and multiplexer also we have done previously. Just we have to call into this program according to the connectivity. Okay. So do we have any kind of internal signals required here? Internal signals are required here. Where is this one? The output of the multiplexers are nothing but internal to the circuit. We have to mention the wires for them. Okay, 4 internal wires we have to consider, right? Okay, why not y1, y2, y3, something. Okay, okay. So therefore, but behavioral modeling is very easy. So I'm going and write the behavioral model. Let's write a module. What is this one? USR underscore 4-bit. Okay. Next, what are the inputs here? But simple case, I'm writing the D here, not DIN. Okay. Next, what is another input? SIL, SIR, selection line, clock. Okay, better I have to, first of all, better always please remember, this is the way it's best one. Reset signal, clock signal, data in signal, serial in left, serial in right, serial out left, serial out right, and Q is my out. Okay, this is the usual way that people write. All the variables I need to write. Okay, what is the input for this one? What are the inputs? All the inputs are not the same order, right? Did you observe this point? What are the 4-bit size? Yeah, selection line I have written. Did I not written the selection line? Okay, I did not mention the selection line. Better I have to go and write the selection line here. SCL. Very good. 3 down to 0. D. Another input is Shall we write first this one 2 down to 0? Sorry, not 2 down to 0. I think the system becomes very slow. This is 1 down to 0 of cell. Another input is SIRL, SIR, log, reset. In fact, we have to write the first bit first and then higher order bits left to be right. That is good practice. Okay, anyway, it's not a problem, of course. Next one is output. SIOL, SOR, yeah, very good. It is a ridge data type, right? It must be ridge data type. Next, this is also ridge. 3 down to 0. Okay, right. Next, we have to write always statement, right? Okay, always outputs depending upon what factors. Okay, so very important. Positive job, RST, let me write. Next, positive job, clock signal. Okay, now let us begin here. What is the first statement? We'll write first content of the flip-flop must be make it 0, right? Okay. Otherwise, if it is unknown, means that if whenever you clock up, then all the things will be unknown forever. Okay, you cannot change anything. That's the reason why if RST is true, what will happen? The Q will be assigned with 4 zeros. Okay. Next, else. Here the Q is equal to all are zeros. If the reset is not there, depending upon the clock, something has to happen. Okay. And what we have to do when every positive edge of the clock? Selection line. Okay, we have to check the selection line. If the selection line is so and so, something has to happen. Right. We have 4 options that are there. Better we have to go and write many options, many procedural statements we can use it. Case is the best choice. If you can use it, ternary operator, we can use it. But the simplest one is case statement. Okay. Case of selection line, right? We have to write the case. Case of selection line. Okay. Okay. So what is this first case? The first case is if 2-bit of 0, 0 of the selection line is there, then what has to happen? The Q is assigned with what? D. As simple as that. Right? Good. What about if 2-bit of 0, 1 is happening? Left shift operation. We have 2 options that we have seen, right? Either the concatenation we can use it or operator we can use it. Okay, better we can go right with the concatenation operation. It's very simple. Okay. Now Q is assigned with what? Concatenation of Q of 2 down to 0 of this one. And here SI L. Okay. Right. Next. If the 2-bit of 10 happen, okay, I have not discussed anything about SOs. SOs, I want to write it later on. SO, I want to write it as the later case. Okay. Now, of course, here also we can write it, but purposefully we would like to write it at the end of the thing. Okay. Now, when the Q is equal to this one, what will happen? SI R, comma, Q of 3 down to next to 2-bit of 1 Q is assigned with Q. Okay. But default, for the default option, that is also, let me write for the any option also, I don't want to change, keep it like that only. Okay. Right. And this is the AND case. So this AND case is belongs to whom? This case procedural statement is belongs to whom? Else statement. This case statement is belongs to whom? Else statement. Okay. If the RST is not there, then we have to go on to the else statement. For every positive edge of the clock, it will be looking at the selection line is there or not. If the selection line is there, then according to the things that will be happening. Okay. So now this is ended here. Okay. The behavioral statement is completed. Behavioral statement is over. Okay. Now I'm going to write the assignment statement here. Look at this one. Assign. There are the two options that are there. Q is assigned. Sorry. Yes, O L is equal to SOL is equal to Q of 3. And assign S O R equal to Q of 1, Q naught. Okay. And finally, and this module. Okay. Semicolon is not required. Look at this one. Okay. In this particular situation, I need not write the register data type. Okay. Because I have used SOL and SOL and SOR outside of the always block. That's the reason why you did not mention this one. Suppose, and here I'm using the non-blocking statements here blocking statements. Okay. Therefore, definitely when we talk about the assignment statements, we have to go and type by using the blocking statement. Whereas in the always statement, we always try to write for the modeling of the sequential circuits, sequential assignments, we go for non-blocking assignments. This reason I have told you previously also. Okay. If you told me that if you're not happy with this, the way that I have written here, then you can write it keeping the SQL inside of the circuit also. But you have to use non-blocking assignment. Okay. This is perfectly all right. We can do in this way. So let us take one simple example, the test case. For example, we'll give you one test case and how it will work. Okay. For example, if you apply 0, 0 here, okay, that means there is a no RST. There is a no RST. Okay. Initially, we have done somewhere, then we keep it low. Next, we have applied the positive edge of the signal. During this clock edge, then we have a selection line here. The selection line here is actually, for example, 0, 0 I have given here. And during the entire time, I have given this one, assuming this way. What is this? Okay. What you can expect now in this duration? Whatever D is there, then D will be assigned. We're assuming that the D is a 4-bit of 101 you have given. Okay, that will be transparent. This is what the Q. Of course, the D is actually, for example, is a 4-bit of 1010. So that will be transparent, as you know very well. Okay. Now, what I'm going to do, now I want to change this one after some time. Okay, of course, let me take it here. We have an option. After some time, for positive edge of the clock, I have given 0, 1. What will happen? Okay, so look at this one. The 0, 0, if you give, and it will come here, the RST is not there, therefore this statement is not executed, and this statement will start executing. Here you see the selection line is belongs to whom? For this case, this belongs to this one. Okay, that means please remember, always remember that this statement and this statement parallelly executed. Okay, how many statements in this program? If somebody asks you how many number of statements in this program, you should say 3 statements. One is always statement, 2 are assignment statement. Total 3 assignments. All these 3 are executed parallelly. That means that what you can see, what do you mean by parallelly? So something like this. So this is the statement 1, ST1. This is called statement 2. This is called statement 3. Okay. So according to the first statement, what will happen? 4-bit of 1010 is assigned there. What is the second assignment? During that time, what is the value of this one? Because this value is not assigned at, okay, is it unknown high impedance state or some value will be assigned to it? Huh? Default value. Look at carefully and tell me. At the same time, all the statements are executed. This statement is also executed at the same time. Okay. Therefore, whatever the Q3 is there, that Q3 will be assigned to the moment this is actually assigned already. Okay. Because if it is available in the same begin and end block, okay. For example, if you see that, okay, something like this, Q is equal to Q1, for example, Q1, Q2 is equal to Q3, for example, Q4 is equal to Q3 as example, then you have to think about it. Once it is completed, then only it will go here. Once it is completed, then only it will go here. Okay. Am I right? But actually, this is available in one particular block, one particular statement. This is available in another particular statement. If this is available in another particular statement, then all these are executed simultaneously. All these are executed simultaneously. Therefore, immediately, the value of the SOL is actually Q3. What is the Q3 here? 1 will be assigned here. This one is 0 will be assigned there. Okay. The 1 of this one is belongs to this one and 0 is belongs to this one. All these are available outside different statements actually. If they are at the same place, for example, same begin and end block, then it won't be the case. Okay, right. Okay, next one is suppose 0 1 is there, for example, 0 1. What will happen for the 0 1? And this statement will be executed. According to this statement, what will happen? For example, SIL is 1 అనుకుంటున్నాం. For example, this is a 1. And what is the content of this flip flops already? This is actually 1010 is already available there. Or otherwise, you can upload somewhere or something also. If I'm not changing the D value, for example, keep it same thing, then it will be stored here is 0 here, 1 here, 0 here. That means this will be shifted, this will be shifted, this will be shifted, right? Okay. Now, during that time, what is happening here? Whatever the Q3 is actually, what is the Q3 here actually? What is the Q3? Q3 is actually, what is the information that you can see here? Okay, the first statement is executed is what? 0, 1, 0, 1. Okay, now what is happening here? This 0 will be captured at this place, and that 1 is captured at this place. If you want to keep whatever the left information is there, then keep this particular statements inside of the block. Okay, then just immediately whenever it is taking, whenever it is coming out of that one, that will be captured. Okay, that's what we have to think about. Like this, we have to understand about the step by step. Of course, when you are doing the simulation, you can understand that one, what will happen. Please experiment this one. Keep this assignment statement inside of this block. Okay, that means you have to write, this is another statement you have to write. And here also you have to write another statement. Check it, what will happen. Hopefully catch this point, right? Okay. Please try to write the test page for this one also. Yes, that will also will changes immediately because all are concurrent statements. Okay, at the moment there is any change in that one, that values will be captured. Okay. See, look at when these particular statements will be executed. Okay. Whenever you are given the selection line, then only the output is changing here. The moment the output is changing means that this by default, these values also will get changed. Okay. This is called implicit way of writing the sensitivity list here. So whenever there is a change in this particular one, this statement will be executed. Whenever you find the change here, this particular statement will be captured and will give you that one. Okay. So when these particular things are changing actually within the always block. So that means selection line is given, the output is changing. The output is changing means that by default there is a change is observed. At the moment of the time, this assignment statements also will get changes. Okay. So that's what it is. Okay. Now let us go and look at very quickly another one also. Okay. Linear feedback shift resistor, 4-bit LFSR. So what is this linear feedback shift resistor? Okay, it is a linear feedback shift resistor. Okay, what is the purpose of this one is, it is used as a random sequence generator. Random sequence generator. Generally, what do you mean by what is the importance of the random sequence generator? Okay, for example, when you have designed some circuit, for example, okay, it needs, for example, 5 combinations to test the one. Okay, for example, eight combinations. For example, you take a full adder. For example, how many combinations you have to give to verify that one? 7 combinations. Okay, so from the knowledge of randomization, okay, if you want to thoroughly test this full adder, you need not apply 8 combinations. Instead, you can apply very essential combinations. Okay, the random. For example, 0 after 0, you'll get 1. After 1, you apply 2 apply. After 3, 4, 4, 5, 5, 6, 6 to 7. That's how we have to go in sequentially. From 0 to 7, sequentially will go. But instead of doing that, okay, 0 after 1, after 2, after 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, something like this. You apply randomly also. You apply randomly. That means after 0, you apply 2, you apply 1, then 7, then 5, then 4, then 3. Okay. Then, for example, what is this? 6, for example. You can also apply. This is called randomization. Randomly apply the input signals and get the output. But the upper one and lower one doesn't have any good sense, right? Okay, because both are the same. It expect except the sequence is different, but both are the same. Okay, but why we don't go with this kind of approach actually? For example, the input combinations, for example, 2 power 5, for example, or 2 power 6, for example. Okay, then it is very difficult to apply the randomization also. Okay, instead, what we can do, you take few combinations, random combinations, and apply. That means that if you want to verify this test, for example, 0 after 2, 2 after 7 is more than enough to verify this particular block. Okay, not that pure random signal. It is actually a pure random signal. This is called pseudo-random. Pseudo-random. Okay, you do not worried about to apply all the possible combinations. You write only few things which are very random in nature, and then can apply. Then you will get you are able to test that one effectively. Okay, it is possible to test that one effectively. Of course, the solution for this one and proof for this one is not there in the syllabus. I'm not going to talk about it, but this is there. But you can identify also by applying this particular random input. Okay, we are able to test that one effectively. Okay, so that purpose we are going to use LFSR. If you want to get this randomization by using the counters is not possible, later we are going to see. That is also possible, but less hardware is required if you're using the linear feedback shift register. People were used to counters actually to generate this random sequence. But instead, we use the LFSR with less hardware. That's the importance of generating the random signals or random test patterns by using the LFSR. If this point is clear, this is the essential purpose of using the linear feedback shift register, generating the random signals, especially the pseudo-random number. Okay, so there are the two ways that we can to realize this one. Okay, there are the two ways. The first one is called external LFSR. External LFSR. The second one is called internal LFSR. Okay. What do you mean by external LFSR? Okay, something like this. It is simply a feedback resistor, undoubtedly. Okay, look at this. For example, 4 flip-flops. Generally, we take the D flip-flops. Okay, 4 flip-flops we consider. And this is called, for example, F0, flip-flop 0, flip-flop 1, flip-flop 2, and this is the flip-flop 3. Okay. So we take the output of this one. For example, here is a D, Q. D input, Q input, D input, Q input, Q output, D input, Q output. Okay. We take the output of this one and connect as an input to it. Okay. And take the output. This one is in this way. Connect the output here. Connect the output to the input here. The output of this one is connected here. And take this output and connect it as an input. It's simply a, the feedback resistor actually. It is shifting and then feedback. Okay. But this kind of thing cannot give you the best solution. But instead, what we have to do, we are going to apply something here. Okay, that is called an exclusive OR gate. Okay, don't apply this directly F2 output into the Q2. Just use the exclusive OR gate. Okay, not only that one, but the exclusive OR gate is a two inputs are required, not single input, right? We take another input from here. This is called tap coefficient. Apply one input here. Okay. Something like this we have to apply. So similarly, this is applied to all the things. This is called tap quotient. And here we have to use one exclusive OR gate. Here use the one exclusive OR gate and one tap quotient. Okay. So that means whenever the TC tap quotient is 1, Babu, tap coefficient. TC stands for tap coefficient. It's a tap coefficient. Okay. So depending upon the tap coefficients, we can generate a random signals. Depending upon tap coefficients, we are able to generate the different type of random signals. Okay, the tap quotient is nothing but whether we need to take this Q3 into this one or not, that we have to check. Okay, if you see carefully, for example, what is the D3? Can you observe? What is the D3? D3 is actually Q3 and exclusive OR with Q2. Did you agree with me? Okay, provided this value is there if the TC is equal to 1. All right. If the TC is equal to 1, this will be the input for this one. Or otherwise, if the TC is not there, then directly this is D3 is actually Q2 only. Okay. Of course, this is depending upon the output signal Q3. That means the clock signal. Whenever the clock is there, transparency is there, right? So I'm going to talk about the Q3. So what is the Q3 output? Can you please let me know what is the Q3 output? It is actually in its own Q3 as well as the previous Q2. The exclusive OR gate, we'll give it this one, depending upon the tap quotient. If the tap quotient is 1, means that what? The tap quotient is 1 means that it is a short circuit, nothing else here. Okay. So therefore, like this, we have to take all these things. That means if we observe this one simple thing let me consider. Let us consider this is a hardware. Copy. Let me paste here. Okay. So if I take this is the tap quotient is something, I'll remove this one and directly I'm connecting this one. Okay. What does it mean? All the tap quotients are equal to 1. Okay. Because of this one, some kind of random signals will be generated. Okay. For example, if you take only these two, for example, you take only the this is, for example, let me consider this is the 2, for example, this is the 1, this is the 0, for example. Okay. You only consider TC2 and TC0. Okay. Then you will see this one. This particular circuit will give you different kind of random signals. Are you getting the point? Okay. So that is like this, depending upon the tap quotient, we are able to provide the different type of sequences. This particular one is called, that means the linear feedback shift resistor is actually depends upon one equation called characteristic polynomial. Characteristic polynomial. What we can call it as characteristic polynomial. This characteristic polynomial tells us that where the tap quotients are available. Where the tap quotients are available. For example, look at this one. This is called x to the power of 4 less x power 2 plus 1. Okay, this is what the characteristic polynomial p of x, let me consider. What does it mean? So look at this one. This is what actually called as x power 4 line. Okay, this is called x power 3 line. This is x power 2 line, x power 1 line, x power 0. Okay. So what does it mean here in this case I'm writing? If I'm writing x to the power of 4 means that that particular line must be available. Okay. Therefore, definitely I have say that this line must be there. And what is the actual equation for this one? There should be x to the power of 4 plus 0 into x to the power of 3 plus 0 into x squared plus 1 into x power of 0. This is what the meaning of this one, right? Did you catch this point? Okay. That means that we don't want the connection for x3. We don't want the connection for, okay, we don't want the x3 connection is not required. Okay. Therefore, x square is required. I'm so sorry. According to this one, x square is required, right? According to this equation, above equation, 1 is required. Okay. Now, how do I change this one? What is this equation? This is not required. But what we need, this is required. X power 1 is also there, no? Okay. I'm so sorry for this. What is this? 0 into x power 1 plus 1 into x power 0. Okay, I'm so sorry. This is right one. Okay. So accordingly, x square is required. X power 1 is also not required, right? This is also not. This will give you the some kind of random sequence. If this point is clear, what is the characteristic equation? Characteristic polynomial. Characteristic polynomial will tells us that where the tap quotients are available. Where the tap quotients are available. Okay, that is defined by the polynomial equation. Okay, just they will give you the polynomial equation accordingly. You have to design the linear feedback shift register, either external or internal. You have to go in this way. One important point you have to remember here is we should not, and we should load some data into the registers, right? Okay, we should not load zero zero pattern in the LFSR. Okay, we should not load all zeros of the flip-flops in the LFSR. If we do that one, forever you will be there in that particular sequence. నువ్వు ఎన్నిసార్లు లెక్క అప్లై చేసినా కూడా జీరోలోనే ఉంటారు, బయట రారు ఇక్కడ. Okay, that means as you can see here, for example, in this case, for example, it's 0, 0, 0, 0. What will happen? Look at this one. What will happen? If it is 0, this is 0, this is 0, this is 0. We have a clock signal. We have a reset signal. As we know that we have all these things, right? This is the RST signal and clock signal. The moment if you, what is happening here? If you apply the logic 0 here, 0, 0, 0, 0. This is called Q3, Q2, Q1, Q0. What will happen to the Q0? The moment if you apply the clock signal, what happened to the Q0? This 0 will come, right? This 0 will come and sit here, right? Okay, what about this 0? What about this 0? This 0 will go and sit here, right? What about here? It will come. This existing 0, this 0, previously available 0, and that come is 0, will come here is again 0. Okay, then this will be shifted. This value is shifted here, and that value is nothing is there, then 0 will be occupied this position. This will be 0. This is forever 0. Am I right? Whatever the tap quotient you take doesn't matter, but it remains in the 0 state. So therefore, we don't try to keep that all the transistors, all the flip-flops into 0 state. Okay. So therefore, it is better choice is this. We can use other than 0. Okay. You can use all ones you can take. All ones you can take it. Or whatever all the 18 or 16 combinations that are there, you can fix it somewhere. In Verilog program, how can you fix this value? So anyone can tell me? Just I want to fix some data inside of the flip-flops. What statement is we can use? If the reset is equal to 0, if the reset is equal to 1, what will happen? We put all zeros. Instead of that one, if your reset is true, you keep some value. Q is equal to some all ones or some other value. That is the way wisely that we have to provide the data. స్టోర్ చేయాలంటే ఏం చేసేవాళ్ళు మీరు? ఫస్ట్ ఫ్లిప్ ఫ్లాప్స్ కంటెంట్స్ అన్ని 0 చేసేవాళ్ళ కాదా? తర్వాత క్లాక్ ఇచ్చినప్పుడు డేటా అనేది చేంజ్ అవుతుంది. రైట్ ఆర్ నాట్? ఇప్పుడు నేనేం చెప్తున్నాను, నాకు ఏదో డేటా దాంట్లో ఉండాలి. ఫస్ట్ ఆఫ్ ఆల్ దాంట్లో డేటా ఉండాలంటే నేను ఆర్ఎస్టీ ఉంది కదా, ఉపయోగించుకుంటాను దాన్ని. ఆర్ఎస్టీ ట్రూ ఉంది అనుకోండి, ఐ కీప్ సమ్ డేటా ఇన్సైడ్ ఆఫ్ ఇట్. అండ్ దెన్ డిపెండింగ్ అపాన్ ద క్లాక్, depending upon the clock, depending upon the circuit, it will be changes the values, right? Okay, look at this one. If suppose all ones is available here, what kind of sequence, random sequence can be generated? Let us verify this one, then we'll come back. This is the polynomial equation I have given. I ask you to generate the random sequence manually. Later we are going to write the program, and then the program will give you that one. Hello. John, what is the first? What is the next sequence? This is the 7 number I have given. Sorry, this is 15. 15 or 16? Is it a 15 or 16? It's a 15, no? It's a 15 number. 2 power 4, 8 plus 2 power 3, sorry, 2 power 4. What is value? 2 power 3, 2 power square, 2 power 1, 2 power 0. This is 8 plus 4 plus 2 plus 1. That is 15, right? Okay, so what is the next one? What is the next sequence we'll get? So definitely this will come here, right? Come and sit here. That is the one. What about this one? This one will go here. Okay. So therefore, this value becomes 1. And that 0 will come here, right? That once it is coming into this particular one means the available information will throw it out, right? What it thrown? 0 has thrown. Okay, that 0 is available. And now this 0 will throw here also. This is a, I'm so sorry, not 0. What is the information is there? Extremely sorry. Now what is the initial one? 1, 1, 1, 1. Okay. Now, because of this one, this will thrown here. This changes to 1 again, but this is 1 here. And because of this one, this is thrown here. It will occupy that one. And this one come at this place. Sorry, not that place. This one come here. Okay. This is already shifted information. This is taken from the previous one, and this is whatever the existing one that will be thrown that is available here. This one and this one, what will happen? What is exclusive OR for 1, 1, 0? 0 will come here. That 0 will be occupying this position, and this one will come here, right? Okay, and this one will change this one here, and therefore the 1 will be remain at this point because we have not applied the clock. Second clock we have not applied. Okay, therefore for the first clock pulse, this value is 0, 1, 1, 0, and this is the 1. So what is this information? What is the 15? What is the value of this one? 13. This is a 13. This is 8, 8 plus, sorry, it's 11, right? It's 11. So 15 after 11 it has come. Now this is what the sequence, now this is what the information that is available. Apply the next clock pulse. Okay. Again, I'm giving this one. Just I'll write to in one sequence, then I will stop this one. Okay. Now apply the second clock pulse. What will happen? This one will come here, right? Okay. And this is occupying this one. This one will come here, and this can change this one. Okay. Then this one will come here. Again, that is, therefore this is 1 and 1. That is change here to 0. This 0 will occupy this position. Therefore, this is a 0, 0, 1. Okay, the next sequence becomes 3. Like this, it will go, and it will come again 1, 1, 1. Okay, it is again come to 1, 1, 1. Please try to check in the next class how many clock pulses we have to apply to come back to the 1, 1, 1, 1. Okay, I told you the two clock signals I have given. How many clock pulses are required to come back to the original position 1, 1, 1, 1? Definitely it will come. Let's check it. Check it once. Okay. It may be 4, it may be 5, 6, or 8. So whatever it may be. There is a possibility, 16 possibilities are there. Then check it whether 2 or 3 are 2. Definitely it's not possible. So I have seen that. Other than 3, 2, then what is the value? Okay. Now, of course, I have given all the theory about this one. Okay. Again, let me just 1 second. Okay, let me go and think about this external LFSR. Okay, external LFSR is also similar. Okay, copy. Okay, it's a very simple, but only one thing is that the internal LFSR is far better than the external LFSR because of some reasons. Okay, because the frequency operations and so many things that are there, but I'm not going to do that kind of thing. So look at this. So we have to use the exclusive OR gates on the feedback path. We have to give the exclusive OR gates on the feedback path. Then can you please tell me where could be the tap questions? And tap questions directly we connect అవుతా ఉంటాయి. Okay. Here we should have a tap quotient here. Easy. That quotient positions will not change. TC1. These are the TC. Okay. So this is connected here. This is connected here. This is connected here. Tap quotient. Okay. That means if you want to get this input, what are the things here? For example, if you want to get this particular signal, what it has to do? We have to take the Q2 and Q3. If you want to get this one, anyone tell me what is this? Please చెప్పండి. If you want to get the signal here, for example, T1 ఏమవుతుంది, T2 ఏమవుతుంది, T3 ఏమవుతుంది అడిగాను అనుకోండి నేను. What will happen? You can see. What is the T1? T1, I can tell you that it is a Q3 exclusive OR with Q2 అని చెప్పాను నేను. What about this one, Q2? Huh? Q3 XOR Q2 దానికి XOR with Q1. What about here? ఎక్కడే వస్తుంది? T3. Q3, Q2, Q1 exclusive OR with Q0. అది ఇక్కడ లోపలికి ఇంకేం లేదు, డైరెక్ట్ గా ఇట్ ఈస్ షిఫ్టింగ్ దట్. ఓకే, బట్ హియర్ యూ షుడ్ నాట్, డోంట్ ఫర్గెట్ అబౌట్, యూ షుడ్ నాట్ గివ్ 0 0. డెఫినెట్లీ యూ షుడ్ నాట్ గివ్ 1 1 కూడా ఇవ్వకూడదు దీంట్లో. దీంట్లో మీరు ఏమి ఇవ్వకూడదు, 1. You should not give this kind of seed signals. Okay, but you can, other than these two patterns, you can give any pattern. Doesn't have any problem. Okay, so this is what linear feedback shift resistor. Okay, I've given the structure. I told you that what is the logic behind this one, and please write the Verilog program for structural programming as well as data behavioral model. Okay, so by Wednesday I will see that one. You please check it. Okay, this is, we have spent a lot of time to understand the language, right? You take these particular diagrams for the same characteristic equation. I'm telling you that, okay, you write for this particular equation. Okay, first thing is that for generalized structure, generalized circuit, you have to write. That means it must be applicable for any tap questions. Okay, that is better. Not try to do this one. Please check it for this particular diagram. Okay, so write a Verilog program for this particular diagram and this particular diagram. Don't go for the different type of tap questions. Okay, generalized program I'm expecting. I'll see on Wednesday how you are able to write that one. Both structural as well as behavioral. Only assignment I have given. Assignment is only for structural modeling of the universal shift resistor. Okay, this is not assignment, just for practice purpose I'm giving. If you're not able to write this one, I will tell you. But Please try to do that. Okay. We stop here today and we'll see the other things in the next class.